Welcome back to Dave Does Math from Home. We are on part 2. There we go. Part 2 of our video series on 16.5, where we do triple integrals but round. We finished video 1 talking about how a lot of times double integrals or triple integrals in cylindrical coordinates can sometimes end up as double integrals in polar coordinates after you collapse that z dimension. And it's true, they often do. And we mentioned that two of the big reasons that you would do a triple integral instead of just a double integral in polar, which we already know how to do, is that you can mess with the bounds a lot more. You can have a lot more freedom there. And you can integrate a density function to get a mass. So I wanted to give some quick examples, maybe not quick. I wanted to give some examples of those two things so you can see what those look like. I'm going to start with the starting at goofy bounds sort of situation. So I want to find the volume between the cone z equals r and the paraboloid I may not know how to spell the word paraboloid. No one fact check this. Find the volume between the cone z equals r and the paraboloid z equals r squared. So this is we are no longer going from a surface down to the xy plane situation. We are going from one surface to another surface, and I want to see what that looks like. When you're drawing these things, since we're usually just dealing with r's and not x's and y's specifically, I like to draw these things with a cross section of the z-axis going up and the xy plane on the horizontal. So this is the xy plane is flat, and it's kind of flat in a round way. It looks flat to the left and right, but it's also flat coming out of the board at you and going behind the board. So this is a flat plane here, and the z-axis is sticking up out of it, and this lets me consider this as like the r-axis. I don't think anyone else has published this because there's no r-axis. It's an entire plane, but I like to think of the xy plane as sort of the r-axis when you're doing cross sections like this. And so if you are doing this cross section, I think we can pretty confidently say that z equals r is this cone here, and z equals r squared is this parabola. So it's sort of like this space between the cone and the paraboloid that's going around 360 degrees. You may be having flashbacks at this point to something we did in section 6.4, where we took the x and y axis and we cut up the space between y equals x and y equals x squared, and we rotated it around the axis 360 degrees, and we found the volume of rotation using the pipe method, or I called it the pipe method. I think the book called it the shell method. If you're having flashbacks to that from 16.4, great. We are going to find essentially the same volume here in a very different way. I realize now, having just said that, I'm realizing that I'm not making a strong case for why we need triple integrals in polar coordinates, because so far both examples I've done have been throwbacks to other things we've already done before. So we will do more examples where there isn't an alternative way to do it that we've already done that's easier. I just haven't gotten to those examples yet, so please be patient. There is a reason we're doing this. It is important for something, I promise. So, if you remember 6.4 with the shell method, please do that on your own, see if we get the same answer. I actually haven't checked. I'm just assuming we do get the same answer. If you don't remember that method, don't worry about it. We're about to find the superior technique for getting volumes of round things in 3 dimensions. So, I want a triple integral. I want the triple integral. It's a volume. So I need, the volume needs dz, dr, and d theta, and it needs an r. It's not quite a pirate integral anymore because the z in here is kind of screwing this up. It's splitting up the r and the dr, but you still need that r. Don't forget about that r. Dr, d theta. This is area on the xy plane, and then when you multiply that by dz, that's what gives you volume. If you just have a dr and a dz and a d theta, excuse me, you're not going to get volume unless you have an extra r here. So, I need bounds. That's what I'm missing on this integral. This is, my volume is all set up, I just need bounds. Z is going to go, in this case, from the paraboloid. Paraboloid is on the bottom, z equals r squared. Cone is on the top, that's z equals r. So I'm just going to go from r squared to r. dr, we need to know how far out we're going. So we need to know where this is in terms of r. And we can find that where these two things meet. R equals r squared at 0 and at 1. I guess this is sort of the weird thing. If you are doing this cross section and thinking of this as like an r axis, both directions are positive. Because r is always sort of positive out from the thing. So you don't really, when we did polar coordinates, we had this whole big thing about like, what if r is negative and you're going backwards from the direction of your angle? Like, that's fine for pre-calculus, but we're not going to deal with that in calculus. So, r is going to go from 0 to 1. I'm going to put my z equals is here. Z equals r squared to z equals r equals 0 to r equals 1, and theta, as always, is going to go from 0 to pi 2 pi. So this is my volume integral for this shape. Let's start integrating. The integral of r dz is zr, so theta equals 0 to theta equals 2 pi, r equals 0 to r equals 1. This is going to be zr from r squared to r, dr d theta. So theta equals 0 to theta equals 2 pi, r equals 0 to r equals 1 of r squared minus r cubed dr d theta. So once you have these integrals set up, they always evaluate just like all the other integrals. I guess I'll start by coming down here and evaluating this, but I feel like I'm going to run out of room and I'll need to erase something eventually. I guess we'll see. So theta is still going from 0 to 2 pi. We integrate on r and we get 1/3 r cubed minus 1/4 r to the 4th from 0 to 1 d theta. And then theta will go from 0 to theta's 2 pi, and we can plug this in. This is going to be 1/3 minus 1/4, I think should leave us with 1/12. 1/12 and when we plug in 0 we get nothing, so this is just 1/12 d theta. And then of course when we evaluate the constant d theta from 0 to 2 pi, you're effectively just multiplying this thing by 2 pi, and we get pi over 6 cubic units is the volume of this shape. If you were following along doing the old Calc 2 method of volumes of rotation, great. Let me know in the comments whether or not it matches. I think it probably does. If you were not doing that because that's old and busted and this is the new cool technique that you want to use instead, also great. We're at 10 minutes. We can do another one. Okay, so I mentioned that the other good reason that we would use triple integrals is for stuff like density. So I want to do an example of a density thing. So I want to find the mass given in the following integral. So our integral is going to go from theta equals 0 to theta equals 2 pi. Doing the full circle all the way around. Oh, I should r dz dr theta. I want to have these written out before I start filling in these bounds. I want r to go from 0 to 2. I want z to go from 0 to 4 minus r. And the density function that we're going to integrate is 3 plus z over 3. So before we start integrating, let's talk a little bit about what this means. We saw from our first example in the first video that these bounds are going to be cone-like. From z equals 0 is the xy plane, up to z equals 4 minus r is a cone that peaks at 4 along the axis and then just goes out linearly as the radius increases. But we're not doing the entire cone. If we were doing the entire cone, r would go from 0 to 4. We're only doing the inside cylinder of the cone. Like someone took an entire cone and just shaved off the outside edge so that it was a cylinder for a while and then it was topped with a cone. It's like cylinder with a cone on top. Radius equals 2 here, and this is z equals 4 way on top. So this is probably z equals 2. That's the shape we're dealing with, and we're going all the way around up theta. So this is a visual of the shape we have. R dz dr d theta, this is my volume, and this function right here, this is my density function. And so when you multiply the density function by the volume, that gives you the mass, and then you integrate across all the different points, and that gives you the total mass of this object. This density is 3 plus z over 3, so this is just sort of increasing as you go up. So this is going to have a very heavy point and a much lighter. So the density doesn't depend on r or theta, it only depends on z. So the bottom layer down here will have a density of 3, and the top layer right here will have a density of 4 and change. So that is the situation. Let's just start doing the math. We're already at 15 minutes. We're going to have to do the math real fast. Okay. We're integrating first with respect to z. So we're going to have theta equals 0, theta equals 2 pi. R equals 0 to r equals 2. The integral of this with respect to z is going to be 3z plus z squared over 6. It's all still being multiplied by r. We're evaluating this at 0 and 4 minus r, dr d theta. So theta from 0 to 2 pi, r from 0 to 2. This is going to be 3 times 4 minus r plus 4 minus r squared over 6, all multiplied by r. When we plug in 0 for z, it all zeroes out to nothing. So dr d theta. I'm going to start rewriting up here. Okay. We're still going from theta equals 0 to theta equals 2 pi. We're still going from r equals 0 to r equals 2. And now this mess right here, this is going to be 12r minus 3r squared. This piece is going to give us a 16 over 6r. And it's going to give us an negative 8r squared over 6. And a positive r cubed over 6. Dr d theta. And let me simplify that one more time by combining like terms. And then we can integrate a second time. Okay, so we're still going from 0 to 2 pi, and we're going from 0 to 2 up here. 12r plus, this is 8 thirds. So this is 36 thirds. So that'll be 44 thirds r. This is 4 thirds. And this is 9 thirds. Both are negative, so minus 13 thirds r squared plus r cubed over 6 dr d theta. We are now ready to integrate. Still good on time. 18 minutes and change. 19 minutes basically. Okay, so still going from 0 to 2 pi on theta. This is going to be 22 thirds r squared. This is going to be 13 ninths r cubed. This is going to be r to the 4th over 24 from 0 to 2 d theta. There's a lot of fractions going on in here. I probably should have done this problem at all before I videotaped myself doing it. That's fine, we got this. 2 squared is 4, so this is 88 thirds. 8 times 13 is 104 ninths. 16 over 24 is 2/3. So this is, when I combine these two, I get 90/3, which is 30. No, thinking about that is 30. Yeah, so that's 30, which is 270/9 minus 104/9 is 166/9. 0 to 2 pi d theta means I'm just multiplying it by 2 theta, so this is going to be 332/9 pi. It's kind of rushing at the end there because we're at 21 minutes and they didn't want this video to cut itself, so hopefully that was good.